Okay. Oh, how come this? Somehow this one does not work well. Sure. No, anyway, well, I have to use these things. It's a little bit cumbersome. Yeah, I don't know why. It should work. It worked before. It's wrong. Work in the wrong direction. Now, it's really strange. But anyway, with COBOL, everything is strange. If you don't mind, I just use my hand to flip the pages, okay? Then, so this is a quick introduction. So now the next level introduction, a little bit history of the particle physics, how we end up with QCD as a theory for strong interactions. Strong interaction means we're dealing with the hadrons. Then when was the first time we see the hadrons? Well, if you look at the history, then the way it traces back with before the 1920, we discovered the proton. That's the hadron, right? Then eventually we discovered lepton. Then around where you have electron, then also the neutrons, the next one. But what's interesting in the 1950s, we have a bunch of the particles. So that's really the sort of, I say, it's a particle explosions, really lots of them. Then the question is, in 70s, after 20 years, so then you will find that, then you find a bunch of more particles involving the heavy flavors. I will tell you later. So in this case, after these particles, the people try to understand how to make this sense of these particles. Then that was the discovery of the Quark model. I will tell you in a moment. Then eventually we find a QCD because the Quark model does not give you any dynamics how you hold the quark together. So then you discover another level of the particle involving the heavy flavors that's known as the November revolutions. Well, recently, as you know, then we have a new set of particles discovered known as XYZ particles. The question is, should we have another particle explosions? We don't know yet, but could be. Then, so the question is, how do we make sense of all of these? So those are the little bit history. So then we say, okay, theories never stop. If you have some phenomena, theories will work on it. So say it's very early, in 1933, we noticed the nucleons are not elemental particles. We know the electron is known as elemental particle. Nucleon, meaning the proton, neutron, have to have internal structure. How can you tell? Well, that's lead to Nobel Prize, because they can measure the magnetic moment of proton and the neutron. As we learn from direct theory, that if you spin half particle, if you're point like, this magnetic moment, the G is equal to 2. Well, you find the proton is not equal to 2, and the neutron has no charge. Then there should be 0. Well, it's not 0 either. So that means that the proton is composite particles, cannot be the point like electrons. Then further, we find that there is a nucleon have to have internal structure in addition to just say, okay, the magnetic moment not equal to G, not equal to 2. So what I find is they do the elastic scattering electron on a proton. Normally, you will measure the form factor. You have a charge distributions. Then you will find that the charge distribution for the neutron is 0, right? Well, you find a very intriguing charge distribution. There must be the internal structures. Then those are the history. Then now led to the Quark model, which is invented by Gell-Mann in the 60s. Then what the idea is very simple. They say, well, proton and neutron are not elemental particles, but they made of the spin half point-like particles known as quarks. So that model is very simple. The proton made of 3 quarks, 2 up quark, 1 down quark, neutron made again 3 quarks, 2 down quarks, 1 up quarks. But the quarks spin half particle but with fractional charge. By that time, nobody dared to say there is fractional charge. Everything is measured by electric charge, the charge of electrons in the units of that. Well, Gell-Mann said it had to be fractional. Then his idea is very simple. Ooh. To my great surprise, suddenly work a little bit, but doesn't work well. So what the idea is they say, well, actually there's 3 quarks. Up, down strange, they put in the flavor, different type, they call different flavor. SU3 symmetry, if you neglect the mass difference between those 3 quarks. Then he said the quarks other elements, then the proton neutron composite. They are corresponding to the so-called the eigenstates of the fundamental representation of SU3 in terms of certain quantum number. We know that from SU3, most of you probably learned, there's 8 generators. 2 of them can be diagonal simultaneously. That means you can define those states in terms of those 2 quantum numbers, known as isospin and hypercharge. So you will find this basic vector for the eigenstate defined in terms of quantum number, isospin, and these hypercharges. Then you will find that one is 1, 0, 0, naturally is a half, 3, 1/3, then that's a down. Okay, we use up quark. Down quark is a minus half, and the 1/3 for hypercharge, then the strange quark. So that's how he started. Now you can see from this magic how he built up the proton and neutron in this very simple model. Well, we now put in the space, isospin, and the hypercharge. Then 3 quark crystals, 3 points on the phase space. Those are 3 states. Then the corresponding, you can build up the baryon number, define that. Then you have a strangeness, the hypercharge minus baryon number. Then the electron charge is defined by this isospin plus the hypercharge divided 2. Then those are the quantum number, which is exactly for the quarks. Then you can do the anti-quarks. From these, you can build up all the particles known at that time. So he said mesons. What's a meson? He said meson is pion, kaon, all those mesons. So all the mesons made of the quark, anti-quark flavor states. So you will have, they combine it, so quark has 3 flavors, anti-quarks have anti-3 flavors. When you combine 2 together, you can have, from group theory, become the A plus 1. So you combine these 2 triangle together, you will have this state. Then the state can be interpreted, this is purely from group theory. What about corresponding to real physical quantities? You will find in terms of the octet mode interpretation, this 8 is known as octet. You have for the corner, if I say L equal to 0, S equal to 0 state, you have a K-on, you have a K0, K plus. Now is where the pions. This is the pion, the pi 0, pi plus, then K minus, K, then other states. So in the middle, you have 3 states. They all have a 0. So then you can have put in octet. There are 2 versions. You superposition of that, get pi 0 and 8, 8. Then also the third singlet state, this little one, singlet state, gave you 8, 1, or superposition of that 8, 8 prime. So this is a very simple picture. You can build up all the known matter at the time, plus many others. I just gave 1 example. Then you can see the quantum number for all these states. You can spin is a superposition of a quark, anti-quark. As you know, in the quantum mechanics, SQ plus SQ prime, you can have a spin 0, 1. Then you have spin of the meson, it's S plus L, L orbiting angular momentum. So the charge is exactly minus 1, the L plus S. Then you can have L equal to 0 state, the one I just showed you. You can also do the L equal to 1 state, JPC. Then you can have other state you know of. Then at this point, there's no color yet. What about baryons? Well, that's exactly what he said, the proton and neutron made of 3 quarks. That's a baryon number is 1/3 for each quark. So the 3 quark state, from group theory, we put the 3 together. You can have a sum of this state, then the spin, the same thing, you decompose, you combine together, you have lots of states. Well, let's see what happened. Now you can physical state, for example, the one we're familiar with, the neutron, proton, and also sigma and the cascade. Then this is exactly how you combine. Then also you can have the spin 3 half state. And this is exactly, then you have delta, sigma, cascade, and omegas. Well, here comes the problem. This is sometimes problem is bad, but problem is very good because there's a challenge. We have to solve the problem. So in this case, you immediately realize if you look at delta plus plus, if in the ground state, there's 3 U quarks. Quark is declared as spin half particles. They are all in the ground state. Quark have spin half. You only have 2 states. How can you have 3? Then there's a problem. Violate this accretion principle. So then what happened? We need another quantum number. That's exactly how the color came. So what is the minimum requirement for the color, the new quantum number? We at least have to have 3. That's important because you have a U quark in the same state. Omega have 3s state. Then you also have a color with the 3 quark waveform had to be antisymmetric. So if you imagine SU3 color, you have put 3 quarks together. If the color is the 3, again, you have this color state. Then you don't want, because we never see any specific color state, suppose we take a color singular state, then that can be constructed by the antisymmetric tensor. So the baryon wave function be constructed as a 3 quark. Then you have a space part, it's a ground state, okay, symmetric. Flavor part, if a 3 U quark or equal, symmetric. The spin part, you put the lowest energy state, symmetric. How can you get antisymmetry? Well, from color. So that's how you constructed the, this baryon, the wave function at that time in the 60s. Then I give you a complete example. You can work it out very easily. Say the proton. Then wave function is, you have a spin part, this is a spin, you have a flavor part, you combine together, quark is, color is antisymmetric, then you normalize to 1. So you check it, well, that's good, normalize to 1. What's the charge? We know that in quantum mechanics, it's an operator sandwiched between the state. So that's sum of the charge of individual quark, you add them together, equal to 1. So wonderful. What about spin? Well, same thing, quantum mechanics, the spin operator sandwiched between a proton state, then all the quarks are spin half, you do this with, the wave function, you calculate everything spin half, wonderful. Most challenging part, that's how we started, is a magnetic moment. Well, magnetic moment, we know, again, you use the operator for magnetic moment, the individual quark, you have a proton. For the proton, then you will have the 4 magnetic moment for the up quark minus down quark, same thing for the neutron, but we don't know what's the magnetic moment for individual quark. Although we know it's a spin half particle, but at least we know the ratio. The ratio of that from a theory, because they can be, this unknown can be canceled, end up with -2. Then look at from the quantum Quark model, it's a -3 If you do that, then if you think of this point like a particle, then you will find experimentally very, very close.
Did you have to assume the mu d equals mu mu to get that result?
No, it's a 3 Just a second. I only have 2 unknown. You up quark, you down quark. Yes. Then relate to the charge. Then you end up with this ratio. Then you cancel the unknown. Then you end up with these numbers very, very consistent. That was a big success. Gell-Mann received a Nobel Prize for the Quark model. But if you think about it, what's the dynamics? You have 3 quarks. What the force to put them together? No answer at that time. But with this simple picture, you explained almost all the quantum composition of the mesons, baryons, plus a few was discovered like omega, discovered later. So that's wonderful. But where the QCD come? Well, that's a theory. What about experiment? Say, well, you claim proton has internal structure. How can I do the experiment to see them? Well, we know the Rutherford experiment, a long time, over 100 years ago. They say the atoms are made by something, with some charge. Then maybe there are different models, and maybe there's a uniform a sphere or something. But with the Rutherford experiment, you will find send the alpha particle to the atom, a gold foil. You see a good number of alpha particles will bounce back with a large angle. That means inside this atom, they're point-like object. So whatever the alpha particle come in, hit the object so hard they bounce back. Imagine you have like a marshmallow type of smooth uniform ball. The particle coming with energy will go diffract, going through it more or less. So never really hit the back so hard. So that was a discovery in the atom is not made by uniform distributed metal. Rather, you have a very, very hard core known as a nucleus. Then with lots of empty space, with the electron floating around. So people try to do the same. If you have a charged particle inside the proton, spin half, what can I do? I send a charged particle in to hit it. That's exactly electron. I send an electron in to hit the proton. then only thing I'm going to measure, just as Rutherford did, measure scalar electrons. The scale I have is the invariant mass of a momentum transfer known as the Q square. I want to make the Q square so large, the inverse of Q square is so much smaller than 1 Fermi inside the proton. That means I have a probe to see something point-like inside the proton. Then what was the prediction at the time? If the proton is made of, like atoms, uniformly charged distributed quantities, then you expect the electron to go through with some scattering angle. Then if the proton made by point-like particle, just like an atom, you have a nucleus, then you will see lots of electrons going backwards. The cross-section with the large momentum transfer will be large, much larger than this one. So that promoted people to do the experiment, known as a slack experiment, a modern version of a Rutherford experiment. Oops. This thing is so sensitive. What happened? Okay, so here's the discovery, which led to the Nobel Prize. Then this is the spectrum you expected from this kind of distribution. Then what the data shows, when the Q square is large, you expect the distribution falls like a crazy, you will find the cross-section so big. That means just like Rutherford find it, there must be point-like things inside the proton. You hit so hard, you have a large cross-sections. That led to the discovery of the Parton or Quark. You know the history. Gell-Mann said that's a Quark. Feynman said that's a Parton. Two of them argued for years, even until they died. Then, of course, now we understand better. Then, so what happened is, with this, what's the Feynman's picture? Feynman's picture said, well, with a large momentum transfer, if I stay in the center of mass frame, imagine the proton coming very, very fast. If you come in very fast, then imagine you have a quantum fluctuation. You have if you have Feynman does not say 3 quarks, but he says some partons inside it. So you have some kind of quantum fluctuation. That if the Hubble probe had interaction time so short, then you can effectively catch the fluctuations. You will see the momentum of the parton in this direction. The K has a plus momentum in the Lattice component, minus component, transverse component. If things move so fast, typical transverse momentum is the order of 1 Fermi, 1 over Fermi. Then what the longitudinal momentum is the order of GeV, because that's a momentum transfer you have. It's so much larger than the 1 Fermi. So in that case, you can make approximation. The parton's momentum is almost collinear to initial proton momentum, order of Q, so much larger the transverse momentum as well as the minus component. So you can introduce a variable known as a momentum fraction X, define the ratio of the largest component, K plus over P plus, if these things move in that direction. So basic idea Feynman has that because the momentum transfer is so low, the interaction point is so localized, the time is so short, it's a 1 over Q. Typical dynamics inside proton, the interaction between them is the order of 1 over Fermi. That's the size of a proton. So if the interaction time is so much shorter than the time for the dynamics of the inside the proton, you can imagine during that interaction time, the rest of them is effectively frozen. So his picture is the following. So what really happened for this experiment, he said, instead of hit the full proton, you hit a single wall of them, rest of them effectively frozen. So the cross-section for electron on the hadron is approximately equal to the cross-section electron on an individual parton, the same invariant cross-section, multiply the probability, density, integral over whatever momentum fraction, to find this parton. So that's his pictures. So what you measure is effectively equal to the probability to find a single particle localized, that's probability, multiply the elastic scattering between electrons and single charged particles. So with this known as this, he called as a parton distribution, then you know how to calculate electron scatter of a parton with a charge, elastic scattering, so you can calculate very quickly. So you have to how to calculate your electron scatter some parton with some momentum fraction. You square the amplitude, you get a cross section, either 1 over flux, square amplitude, multiply phase space, integral the phase space. You calculate immediately Partonic level is proportional delta function. So momentum fraction has to be equal to whatever x. Then your total cross section is, because delta function fixed that convolution, fixed this integral. So your cross section is exactly proportional fractional charge times density. Probability to find that parton at that momentum fraction. So that's exactly model, the Parton model. It's in the handbook of equation 1.1. So that's the Feynman's Parton model picture. Idea is very simple. You have a very hard collision. Rest of the inside the hadron is effectively frozen. You pick up the one, have hard collision, then you calculate the scattering between your probe and the hard parton, then immediately get your cross-section, multiply probability density to go to all the phase space, you get the physical cross-sections. So that was very, very successful to explain it. Theorists explain it, the experiment, they receive a Nobel Prize. Then also you can, I'll tell you a little bit later, theorists can show exchange particle, that calculation depends on the spin. If you do this calculation, it's a sensitive spin of this particle. As a homework, you can do this scattering cross-section. Assume this is a spin half. Also, you can assume this is spin 0 scalar. Then you immediately derive these two are slightly different. So you do immediately, you can compare with the experiment, then people find it, well, it's a spin half. So by that time, it's discovered spin half quarks. Then you have a Partonic structure, the proton have a Partonic structure. Then of course, the immediate people ask, they have to get, what's the force behind it to hold this together? That led to the discovery of birth of a QCD, which is in fact a combination of the Quark model plus Yamil gauge theory. So that was a little bit history lead to the QCD. So now here's a QCD. QCD is that made of the gauge theory, made of quark field, spin half field with a different flavor. So far we know as 6, and also color. So in the fundamental representation, means the 3 colors. You have a gluons. Gluon carry 8 colors. Then Lagrangians look very simple. You have a kinetic term, mass term, and the gluon interaction term. Actually, gluon kinetic term as well as the interaction term, we mix things together. So I want to compare the QCD with QED. You know the QED. It almost looks similar. Then this is kinetic term. Then the gluon is very different from photon. This is a formula we all know FME for the electromagnetism. But gluon, there's an additional term. When you expand these, you will find the gluon interact among themselves. You all know photon does not interact with photon. That's why inside atom, you can have lots of empty space. You can have a photon floating around, but you can define the quantum orbits of photon because photon does not interact themselves. They have to go through the charge. But gluon is different. It is this difference leads to tremendous difference. So let me quickly go through. There's some basics. I'm not going to spend much time on it. This gauge theory, if you make gauge transformation, then the QCD Lagrange is invariant. And also you will find that because the gauge sensitivity, you have to fix the gauge. Depending on how you do it, you can gauge fix in the covariant way, then lead to the gauge propagator, gluon propagator, depending choice of a gauge. So this is the covariant form. Lambda equal 1 is the so-called Feynman gauge. So now, one thing is important. There's no free lunch. As said earlier, you can choose the gauge whatever you want to. Physical quantity should not depend on the choice of a gauge. But if you choose the covariant gauge, it's very easy to do the calculation. Well, you will find that you lead into the extra degree freedom. That's a requirement of the ghost. What's a ghost is needed when you work in the covariant gauge. So this is the ghost Lagrangian part. Why we need that? Well, I gave you a simple example where the optical theory, you have the scale, just imagine part of 4 scalar amplitude can be written in terms of amplitude square sum over all the state. That's optical theory. Well, because if you do the covariant gauge, you realize if you expand this square, we're not exactly equal to these because this has virtual state. Then because it's a virtual line, so you have to include this gluon's virtual in the amplitude form. You have to have a gauge ghost introduction of the ghost to cancel the unphysical degree of this gluon, so that the imaginary part of the forward scattering amplitude equal to the square of the scattering amplitude square. So that's the need of the ghost. So they have to be careful. If you do the calculation of covariant gauge, make sure you include the ghost. So then in the Feynman rule, the propagator, then also because the gluon have self-interaction, you have 3 gluon interaction, 4 gluon interaction, as well as the ghost. This will lead to the tremendous difference between QCD and QED. So then here we have QCD. Well, next thing I will say, QCD is everywhere. Then imagine we ask a question, where did we come from? We often ask that. When the universe started, Big Bang, there is no proton, no neutron, no people. Only thing you may have is from the elemental particle, quarks, gluon. But how the QCD tells you when the universe cool down, how the proton neutron emerge, then eventually how the people showed up. We know the later part, biology people told us, but what about the original part, early part? We don't know. That's the motivator to do the relative high, having ion collision to study the early universe. Then for us, for this TMD, we consider second part questions. So suppose that we know we are, what we made of that? Well, if you look at the new periodic table for particle physics, here is the periodic table. Here's the we are, everything the neutron that start from the question of how to connect this together. How to understand emergence and the properties of the nucleon, nuclei, in terms of the elements of the modern periodic tables. How the gluon, the little one here, glue everything together. Those are the really difficult questions, most interesting question of strong interactions. Then we have facility, CBF, LGC, AMBER, the UIC, try to study that. There's a new term has been used in the last 10 years, known as the nuclear photography, is in the sense a branch of the strong interaction to search for answers to these questions at the Fermi scale, at the scale of the hadrons. So then the question is the color. Color is very different from electromagnetic charge. Although it's in some sense similar, it's just quantum number, represent the strength of interaction of the strong interactions. Well, color is confined, unlike the electron photon. Because that we don't see any quarks and gluon in isolation, the structure of nucleon nuclei, the emergent property of QCD. Then even more consequence, if you look at the spectral landscape of the QCD interaction, this is the area where the nuclei and the nucleon, this is the area we studied in the LGC in the asymptotic region, then the QCD works well, but this is the most rich part of the QCD. We try to understand the structure of the nuclei, how they emerge from QCD dynamics. Then one thing I want to put in your attention, we all know this, atomic structure, Rutherford told us that is the core. The distance size of the nucleus is 10 to the 5th power smaller the size of the atom. So lots of empty space, electron floating around, you have quantum orbits. You don't have this in QCD because the gluon carry color. I take the most close example, the B metal. You may have a heavy quark or anti-quark, have a light quark floating around. It sounds like a hydrogen atom. No, you don't have this quantum orbit because they exchange the force, the gluon carry color. Gluon can flag into the 2 gluons, the cucumber pair, or the thing. So it's a brown mud. So the structure of the hadron is very different from the structure of the atom. So those are the things that it's challenging for us to study. So how can we study them? Strong interaction is so strong. When the theory was proposed in 1973 or the end of 1972, not many people paid too much attention except this guy, Frank Wichak, as a student. Then David Gross gave him the problem. And David Paul at MIT got a problem, at Harvard got a problem. Try to study how the interaction vary as the scale you probe them. We know in the quantum theory, the strength of interaction is not fixed, depending on how you probe them. So they studied evolution, eventually discovered asymptotic freedom. So that means the interaction can be very weak at the shorter and shorter distance. So theory approach to strong interaction that can be break into several approaches. One is known as the Perturbative QCD factorization approach. I factorize the physical quantities, say electron and the proton, into some short distance probe. I can calculate, multiply some distribution like a Parton model, but in QCD, I'll tell you how the definition, then multiply some corrections. So this is approach is make an approximation of the Feynman diagram level. That's the one we spend most of time, last 40 years. Then also the effective field theory approach, for example, does make approximation Lagrangian level, known as soft Coriolis effect theory, and QCD, and many other effective theory, Archival perturbation theory. So you expand your theory at the level of Lagrangian. Then also Lattice QCD. Lattice QCD, in the sense I make approximation of spacing. Instead of I have an infinite universe, I break it into the grid, then there is some size, then I can calculate, put on the computer. So the only remove, so this constraint approximation is the computing power. But this can be due to the very sort of first principle, the perturbative, sort of non-perturbative calculation. Then also there are model many other approaches. So this is a major approach to study QCD, all of them involving perturbation. That's what I want to say. So now we will concentrate on the perturbative approach because we can control, we can calculate them. So the reason behind it, because asymptotic freedom, they discovered that the strength of interaction actually going down as a function of the momentum transfer. The number they can go to the 10 to the minus 1, although it's not the 10 to the minus 2 like 1 over 137 for the phi structure constant, but at least this is sufficiently small, we can do the perturbation theory. So now, when you do the perturbation theory, start to calculate diagram, you learn there are a few concepts. I will use a few slides to summarize them. Those are very important concepts. Number one is the renormalization. You heard about it. When we calculate diagram, immediately find if E plus minus to exchange a photon or gluon, then go to E plus minus or the quark, anti-quark. Then immediately realize you have this kind of loop diagram. You have this loop correction. Then if you integrate over this loop, you get infinity. What's going on? I try to do the perturbative expansion, I end up with infinity. Even though I claim my coupling constant is small, but coupling constant times the infinity, forget it. I cannot do the perturbation theory. So well, the idea of the exam, where the infinity come from? The infinity comes from when you integrate over this phase, you have a high momentum state. There's an energy state. So that means you sum over the states of a high mass, large invariant mass. Well, those contributions correspond to very local behavior of your theory. But we know any experiment, you have a momentum transfer, you cannot see anything smaller distant than the 1 over momentum transfer. So you never really see this state. So that led to the idea of the renormalization. Idea said, well, if this is local, I put them into the local effective local interactions. So I give you an example. So what the renormalization do? Renormalization is effectively reorganization of your perturbed expansion. So imagine this is a diagram. If I integrate the loop, I have a divergence. So what do we do? I'm just subtracted off the term local. So this is a high mass state because mu is some large beyond what I can probe from experiment. So I add and subtract. So that after subtracting that, this part no longer have divergence when the momentum transfer between, because momentum is bounded by this value. Then everything else sounds like a perturbative divergence, but they're local, they're point-like, almost point-like. So then what we need to do for physical observable, For physical observable, you all know how to calculate from left-hand side. You have Feynman diagram, leading order, next leading order, but next you don't have divergence. So what I'm going to do, I'm going to add the subtract. I subtract the high mass state here for next leading order, but I cannot throw them away. It's a part of a theory. I include them into local part. Then in a sense, effective interaction now depend on scale, you probe them. So when you combine this together, so sensitive, my hand is just, see something, I have some kind of magic here. So what happened is that then the new perturbed expansion is not expansion in this way, rather expansion, this combination at the leading order, this expansion next leading order. So it's a renormalized coupling, depending on scale you observe, then also there is no UV divergence. So renormalization is actually the reparametrization of the expansion parameter in the perturbation theory. If you write down the Lagrangian Lagrangian pair, they should be equal to Lagrangian renormalized because you did not change the theory. You just reorganize the perturbation theory. So then what's the consequence? Well, you introduce some scale depending on probe. Then you say, okay, I'm expanding the new perturbed expansion, but physical quantity, you do the experiment. Experiment does not know how you expand it in the theory. So that physical quantity cross-section should not depend on whatever the scale introduced to separate your perturbation theory. So in that case, then they have to be zero. So you lead to the physical quantity will be expanded in terms of the coupling constant with RFS. The immediately derived RFS have to depend on scale your probe. That's exactly the renormalization group equation gives you. That means tells you the strength of interaction depend on the scale your probe. Now you can calculate this beta function perturbatively. You will immediately find that this beta function worth the Nobel Prize because it's different from the beta function for QED. When the QED happens, we all know when you go to shorter and short distance, the interaction getting stronger and stronger. But in the QCD, because this beta function, you find it when you go to shorter and short distance, strong interaction getting weaker and weaker. So then also that, well, you just told me that a quantity you measure like coupling constant or strength of interaction depends on scale your probe. What about Quark mass? What about all these things? Well, in the quantum field theory, all this quantity depend on the scale your probe. So if you the Quark mass will also have, this is a renormalization group equation. You find a dependent anomalous dimension. You can calculate. Here it tells you. But the bottom line is you will find that you can calculate that when the scale goes to infinity, actual mass is asymptotic go to zero. That means for light quark mass is much less than lambda QCD. If you're dealing with a physical observable at the order of GeV or this thing not to go to infinity, then you can treat the QCD perturbation theory is effectively a massless theory for light quarks. So that's a message. For when you're dealing with a QCD, if you're dealing with a light quark, you can, at a high energy experiment, you effectively treat light quark as massless. Well, if you do that, there's no free lunch. If you do something, something will come back to hurt you. So if you set to the say theory effect of the massless, if you try to calculate diagram, you learn how to handle the ultraviolet divergence. Well, come with a massless theory, you have two more divergences you have to deal with. One is known as the infrared divergence, one is the collinear divergence. I'll give you a simple, because you will hear a lot about this through this week. So you take a simple example. I have a, say, quark interacting with something hot, but due to the hot interaction, a particle interact, you radiate, right? You radiate the gluon, but you never observe the gluon. You have to integrate over the gluon. Then what happened to this propagator? You will find that if this particle you observed is treated as massless, p square, k square equal to 0. Then if you do look at this momentum of this propagator, you find a p minus k square actual approach to the p square approach to 0, you lead to so-called infrared divergence. If you all the component of k goes to 0. If the radiation getting small and small, you get infinity. Something's wrong. Yeah, go ahead.
What if the initial particle is not on shell? What if the initial particle is not on shell? Are you saying simply that heat is virtual because the mass is so small?
I tell you, here we're dealing with the calculation asymptotically. It's a treated the asymptotic state. We define the scalar amplitude, they're on-shell particle. If you treat it off-shell, I can tell you, anyone interested, you have to be extremely careful that number of the famous mistake by famous people because they treat the parton off-shell, especially gluon, you break the gauge inverse. You have to be extremely careful. But anyway, here, let's stop here. Saying this is the one possibility when the gluon momentum goes to 0, sounds like a system, no radiation. But if you calculate, you will find this contribution is much bigger than one you start with without radiation, because this is infinity. Just like the ultraviolet divergence, right? You choose the lowest order, the finite, next leading order, you calculate, you find an infinity. That's a problem. So this is the problem we have to deal with. I'll tell you how to deal with it. Another problem for the massless, a k does not have to be 0. If the k is parallel to p, so the gluon is around this direction, even the gluon momentum is not equal to 0, you realize that I take the k is lambda times the p, the lambda is a constant, then p minus k squared is proportional to 0 again. This divergence is known as the collinear divergence, when the k is parallel to the p. That's another problem we have to deal with. You'll hear a lot of factorization. Factorization is exactly the origin of that is that collinear divergence. The infrared divergence is taken care of by the theory itself, if you include in everything at any given order for physical observable quantity, you can prove the all infrared divergence have to cancel among themselves. But collinear divergence, if you observe the particle, that means you know their momentum. So any radiation the parallel to that gave you collinear divergence. That's the one gave you all the trouble. That's the one requires the factorization. That's the exact essence you will hear a lot about this week. So next one is what the QCD can actually calculate, special perturbative QCD. So the idea is that any physical cross-section, you have mass scale and a Hall scale and the factorization scale, or renormalization scale in this case. Now, if you do this expansion, say when the mass scale go to 0, because I say it's, we can treat it as a massless theory, then the expansion, you can say, imagine through over the mass leading term, then the correction term and all the mass of these over the Hall scale with parameters. This expansion is only convergent or valid when the kappa is positive. So we define the quantity known as infrared safe. That means you can apply perturbation theory to calculate. Corresponding to this kappa is positive. So the conclusion that purely perturbative calculation alone, if we try to take advantage of asymptotic freedom, are only useful for quantities that are infrared safe. Now I will tell you a lot in my lectures, and you hear a lot in the whole week. A physical quantity with identified hadron is not infrared safe. So how can you dealing with, say, deep enough scattering cross-section, hadron cross-section, scattering cross-section, people doing it all the time, they're HC? That's what you need to know, learn. So the solution to that, so that's a quantity. So that what I try to summarize so far, the solution to that, if you have identified hadron, they are not perturbative calculable. Solution to QCD factorization. What is the QCD factorization? I said in words. I'm going to give you a very intuitive form example at the beginning of the next lectures. Words that you have different scale involving the collisions. You have a hard momentum transfer, like Feynman did. There is a scale of the hadron itself, order of Fermi. You have a momentum transfer order of GeV. So the factorization is that I'm going to separate the physics between the different scale. Then you have to prove the quantum difference between these two scales is suppressed. So you can neglect them. Cross-section is the probability. Your factorization factor write one probability in terms of product of two probability. One probability at happening at the short distance with large scale. Another probability is happening at distance scale of the soft scale, non-perturbative scale. The correction between them can be power suppressed. That's a statement I will prove to you. So then summarize all the perturbative approach to these. There are three key fundamentals. One is that the renormalization, as we said, which led to Nobel Prize for the gauge theory. Then also asymptotic freedom, because you can go to short distance, strong interaction can be effective weak, you can calculate. That led to Nobel Prize. That's a very important third part if you're dealing with identified hadron, is known as the infrared safety and the factorization. The calculable short distance and the factorization, they can connect the parton to physical, observe the cross-section. They led to the this APS highest theory prize. This is Sakura prize by Mueller and Sterman. So what we try to do is look for infrared safe and the factorable quantities. So that's a first part of the really introduction, how we end up with the QCD and how we could deal with it. So now I'll give you an example before I finish this lecture. I'll start with example, don't identify your hadrons. As I said earlier, if you have an identified hadron, you cannot calculate. It's infrared divergent quantities. Well, what is it possible? There is an observable involving hadron, but without the exactly identified hadrons. Well, in that, because you don't identify them, unitarity help you. So I start with observable cross-section with a, it is a look for two types of physical observables. One is a look for pure infrared-safe quantities. That means I can apply perturbation theory right away from beginning. Another type of observable is with identified hadron. That means I have to find the factorization, I have to prove the factorization to separate the physics at different scale. So this is the whole bottom line of our approach in the last really 40 years efforts. So start with something simple. In this end of rest of my lectures here, you look for the observable, the fully inclusive without any identified hadron is known as E plus minus 2 hadron total cross section. That means you have a, LAP did that. Best 3 now running in the Beijing, E plus minus collide, look for all the particles in the final state. You without specifically tag any one of them. Then the LAP done a number of years ago, they have much higher energy. And also now in Japan, the Bell 2, they do the experiment with E plus minus at the energy of the B meson. What the best in the Beijing is the energy of the charm meson. So those are the E plus minus process. But you can produce hadron in the final state. So what I define observables, I'm not going to tag any specific hadron, but I just integrate over all the possible hadron. Whatever event you find it, have one hadron in it, okay, that's part of my event. Have 2, have 3, I include all of them. In that case, I can show you the cross section to E plus minus total hadron is the same as total cross section E plus minus 2 partons or quarks gluons. Because you eventually prove this quantity, you can calculate in QCD perturbation theory. I start with a simple intuitive argument. I have a scattering amplitude E plus minus exchange of photon, plus minus virtual photon or Z, have some kind of short distance Hawk collision controlled by the momentum transfer Q. Then they produce a bunch of a particle that have a state I label of the M, those are platonic state. But confinement tells you never can have a parton enter in your detector. The parton have to eventually emerge into hadrons. So at an amplitude level, there is a blob, they go end up hadron in your detector, I call state N. So in terms of cross-section probability, I can imagine the cross-section proportion, some of the probability E plus minus to all the hadron. I can write them into the 2-step. The sum of the end in the middle part, the probability is equal to the product of E plus minus to all the intermediate parton state M. Then multiply the probability M goes to M, N. So then I switch the order of integration. That means that whatever have state M with the parton, they have to become the hadron. So I write the sum of the M, the probability E plus minus the parton, then sum of all the probability for M goes to the N. This had to be equal to 1. This guy, because confinement, you never see a free quark and a gluon in your detector. If you produce a quark, if you produce a gluon, they cannot go anywhere but become the hadron in your detector. So if you take this as a 1, you realize this probability plus minus hadron is proportional, the total probability to all the platonic state. So in that case, the cross-section to produce all the hadron is equivalent to the cross-section to produce all the parton. That's a very intuitive argument. I can give you a number of proof, more rigorous. So then with that, I didn't identify any hadron. You start with a cross-section to hadron, you end up with a calculate something to the parton. I don't ask any hadron. Well, so the total cross-section to the parton in the QCD perturbation theory can be expanded as a power series of alpha S and the power series of alpha S with the larger momentum renormalization scale of mu. Mu is the order of a Q. That's only the largest scale. Sum over all the orders. So this quantity is completely perturbative calculable in QCD perturbation theory. If the Q is so much larger than this whatever non-perturbative scale, you will find that this is the quantity, the coefficient you can calculate. It's a completely finite to all order in QCD perturbation theory. People have calculated too many loops for this. So let me give you another better proof. So well, I take advantage of optical theory. what you really have E plus minus 2 hadron in intermediate state M. Whatever it is, if the optical theorem is true, this is just an imaginary proportion, imaginary part of force scanning amplitude, E plus minus to E plus minus, with all the interaction in the QCD. Well, that's a blob. It's a time-like vacuum polarization. So then from a current conservation, QED current conservation, you have all the include weak interaction Z, you have a Q, that's current conservation factor, you have multiplied the constant factor, a scalar factor. So then the question is, if this whole thing can be calculated in perturbation theory, is infrared safe, that means the sigma, this almost a big pi, has to be infrared safe. Although there are lots of hadron in it, well, how can we prove this is infrared safe? This actually, you can think, I'll give you a very intuitive model. What's infrared safety? Infrared safety of this big pi, in the sense there was no pinch pole in the pi, so you have physical quantities, you have divergence. What the pinch pole means, imagine you have a phase space of any parton in this phase, in this loop, inside it at momentum k. You have a k squared is a virtual, parton momentum is always virtual, you never see them real. So imagine you integral the phase space, you end up with, say, there is a pole, you have the upper half plane, lower half plane. That means no matter how you deform contour, you end up with infinity. So that's bad. If you happen that way, that means that quantity cannot be calculated in the QCD perturbation theory. So you try to avoid the pinch singularities. Well, I try to give a very intuitive argument. There is no pinch singularity. You cannot have pinch singularity inside this blob, no matter how complicated. What's a pinch singularity? Pinch singularity, when the k square goes to 0, means the parton, like a classic unmasked shell, flying away. Because that's time-like, you stay in the center mass frame of that virtual photon. You have an invariant mass, Q. If you have two particles, they pinch, because momentum conservation you have to back-to-back, right? They have to fly away. If they're pinched like a real particle, they fly away. What's the chance for them to come back to meet together? Because this vacuum polarization means two particles in, then two particles out. So you have to merge back. If they're really pinched, there's no chance for them to come back to merge together. So that's exactly intuitive picture tells you this blob cannot have pinch singularity. I'm going to give you an example how to show that. I'll start with the lowest order diagram. I have every single step. Say I have E plus minus to a photon go to E plus minus or any fermion pair. So you have a trace of this part square of the amplitude, and the trace of this part of the square, even have a mass of a quark. Imagine this is a quark. Then I work about algebra, end up with this metric Feynman square, depending on mass. Then I'm going to calculate cross-section. So when I calculate cross-section, as you know, invariant mass at the d sigma dt, then they have a proportional to mass square. I work it out at this level. As for the sigma 2 means order of a square, e square, the coupling constant square. You sum over all the flavor possible QQ bar. Then you end up with a constant factor. Then multiply a phase the threshold constraint. So imagine if this heavy quark, if you lose as total energy you in, is not enough for you to produce heavy quark pair, then they cannot be contributed, right? So that's a threshold constraint. With this lowest order calculation, it's a completely finite, no divergence. What happened one loop? If you do that, we say, well, I'm going to radiate a gluon. If I radiate a gluon, then you notice immediately, as we discussed, if the particle is massless, you will have infrared divergence and collinear divergence. How they show up, I put it in a different form. I introduce the energy fraction xi is the energy of the particle you observe, divide maximum the half root s. Then you will find that the x, if you have this relation in terms of angle, the 1 minus x1, for example, is proportional to 1 minus cosine angle. So immediately you realize situation, you can have a divergence. This amplitude can have an infrared divergence when x3 goes to 0, this momentum goes to 0, as we discussed. And also they're going to go to collinear divergence with this angle go to 0. The radiation can come from this side. You can when this angle go to 0. So this at this order, if you only calculate this diagram square, plus crossing, you get a divergence. Well, that's bad. Well, that's not the only diagram contribute to this total cross section. You have to include the virtual diagram. When you include a virtual diagram, you know, infinity minus infinity is difficult to deal with. You have to have a regularization. You have to hold the infinity, not to go to infinity. Then you calculate everything, then you combine them. So one very important regularization you will learn a lot, hear a lot, is dimensional regularization. Dimensional regularization is powerful because that they used to prove the renormalizability of the gauge theory to have the Weltman receive a Nobel Prize. But that dimensional regularization in the same, say in the space-time, instead of 4 dimension, I'm putting to any dimension, a fractional dimension. After I do the calculation, I take the limit, the space dimension go back to 4 dimensions. But it's not arbitrary. You can try to regularize both ultraviolet and the infrared. It's powerful. You can regularize both. But it's not the arbitrary way. So the strictly good way to do it, this is a slide I want to show, make sure we understand how the dimensional regularization work. For observable, so remember we first have to start from here in the region with the dimension less than 4. So we do the UV renormalization. Remember we talked UV is the first one, first to deal with it. So you have this, make sure your dimension go to smaller than 4. You have unrenormalized Green's function or any observable you try to calculate that lead to the renormalized quantity. But I say I didn't change the theory. I just reorganized my perturbed expansion. So after I have expand everything in the renormalized quantity, I'm going to analytically continue my dimension go to the dimension larger than 4. Then in this case only for physical infrared safe quantities. So I calculate this. Maybe I have a real diagram have divergence, virtual diagram have divergence, but with the regularization, neither of them divergent. When I combine them together, the divergent cancel, then I'm safe to go back to the limit. Epsilon is the dimension, you know, physical dimension minus this arbitrary dimension in dimension regulation. Go back to physical quantities, the physical region. But that's only for infrared safe quantities. But if you also say, what if I go into this region? Well, theory have a problem. Then at least we don't have to worry about it for now for the QCD. So I give you an example. Next leading order. I told you I did a calculation in a fixed dimension, have divergence. Real diagram calculate have divergence, have both infrared and collinear. So where I can calculate in the arbitrary dimension in terms of epsilon, epsilon is 4 minus, I use the d is the d dimension equal to 4 minus 2 epsilon. So in that case, a real diagram is completely finite. But you can see if I take an epsilon go to 0, the real diagram have the power square divergence that corresponding to the phase space. You have both collinear and infrared divergence. So that's why you 1 over epsilon square. Then you also have term 1 over epsilon that either come from infrared divergence or collinear divergence. But if you regularize that, everything seems to be finite. I can do the same virtual calculation in the sense of the vertex diagram loop with the loop. You calculate, again, you have this both divergence. Now, before I'm taking dimension go to 4, I'm going to combine them first. If I combine this real and the virtual diagram together, these two divergences all canceled, then everything is finite plus order of epsilon. Then this is infrared safe quantity. I'm ready to take the dimension go to 4. So this term be dropped. So that at the order of next leading order, everything is finite, even though individual diagram is divergent. So the total cross section will have a leading order. Next leading order have a leading, in the sense, the real diagram, 3 particle final state. Virtual diagram is the same as 2 particle final state, but regularized in terms of power of epsilon. Then you combine them together, or the order of alpha square, then you end up with something completely finite. It's a total cross-section infrared safe. Then also the sigma total is the independent choice of the infrared and the collinear regularization. Then people have been doing this to very high order. Last knowledge I learned at least 3 loops. Then this is just 1 loop, what I did here. But you can do this very quickly. Then people find it, no divergence, everything is finite. So you know the QCD perturbation theory known as asymptotic theory. They never really convergence. So you start a theory, have a leading order, next leading order, you have a big behavior is better when you change the scale, because physically never know what the renormalization scale is. So you can change the range of scale. You see the theory has a prediction of some uncertainty. When you go to a certain order, you will see the uncertainty getting small and small. But eventually they will getting bigger. Then the theory go to asymptotic regime. So far, I believe the people already go to the highest order, at least 3 loop, the partially 4th loop. They have not seen, they have maybe have a little bit hint, the coefficient of the next, those order becomes larger. But that tells you how well behave a QCD infrasafe quantities in perturbation theory. So that's a quantity we study without any identified hadrons, even though the cross-section goes to all the hadrons. So how to test it? Well, I mentioned that you can measure the E plus minus to all the hadron, right? Well, sometimes it's good to normalize it. They use, so instead of measure this cross-section, measure the ratio of cross-section E plus minus to E plus minus to mu plus mu minus. That's a QED version. So take the lowest order we just calculate is order of alpha s over pi for light quark. You can include the heavy quark. You can include all the high order. What the message is, you can do the experiment. That's what you measure in the ratio, the known as R. Then you will find that you can have low energy, you have some resonance. Then you have almost flat. Then you go to high energy, you have more resonance, then the closely flat. So what tells you is that prediction from QCD is very good. And also this, you noticed, they're strictly proportional to NC, because the lowest order, the E plus minus to the QQ bar pair, you know that in the quantum mechanics, cross-section proportional sum over all the final quantum number of final state. That if you go to QQ bar pair, QQ quark carry color, they have 3 colors. But you don't know, imagine, you can at least 3. Then experiment, this is actually probably one of the best measurements still to determine what the color. So far from E plus minus, this R measurement, the N is a 2.99 something, very good. Of course, people measure 3 jet event, other jet things to try to test the number of colors. So far, we still have not seen a major disagreement with NC equal to 3. With the last 20 minutes, then what I'm going to do, another example, without identified hadrons. Before next lecture, we're dealing with identified hadron. We said, well, total cross-section is good, it's sum over everything. But here I'm going to do slightly different things. So I'm going to limit the phase space. Instead of integral over all the phase space, I'm going to put the constraint on the phase space. I still don't try to identify the hadrons, but put the constraint on the phase space. That's exactly lead to a second example, lead to the very important observable known as jets. So you heard a lot about jets. I'm going to give you the pictures, very probably different from what you normally think, but actually it's like a total cross-section with the phase space constraint. So in that case, is a jets known as a trace or footprint of Parton. You produce E plus minus, imagine you have a high energy collision, you lead to the QQ bar flying away. QQ bar carry color. There must be soft interaction between them to neutralize the color, but because of soft interaction, you don't change the direction of the jet that much. So that means the events look like you have a beam of a particle going this direction against the beam particle going opposite direction. Those are known as 2 jet events. Of course, you can have situation with 3 jets or other jets. But the question is that, is this quantity perturbative calculable? Even though you have a hadron involved? Answer is yes. Then this is not the trivial, because you have a constraint on the phase space. So in that case, ideal you can have jet in the sense I define as total cross-section with a limited phase space. Then also the idea, the very first one is the divergent cancellation. From the last example I showed, if you calculate the total cross-section with the leading order at 2 particles flying away, that's fine. Everything's finite. But if you go to next order, you have a QQ bar plus gluon. When I integral phase space gluon, you notice there's the divergence. Then the divergence tells you you have to have virtual diagram to cancel. But imagine what's a virtual diagram? E plus minus go to QQ bar pair. Virtual diagram means a gluon loop. That gluon does not affected by any phase-space constraint. They are just like a lowest order. Those two core cube are in the final state, just a gluon. So you immediately realize when you apply the phase-space constraint, you only impact the real diagram because real diagram go this way, then another gluon radiate. Well, you say gluon have to go to along the quark that end up with a jet. So the phase-space constraint only affect the real diagram, but not the virtual diagram. Then how can you have that cancellation? That was exactly debate many, many years ago. That led to the famous paper by Sturman and Weinberg, known as Sturman-Weinberg jet. So definition of a jet cross-section is not to just say a two beam of a particles. You have to have a two beam of a particle plus the phase space over the 4 pi. Because detector resolution, you never can see the very soft particle in all the 4 pi. So you have to integrate over the phase space, that part of a phase space. So you allow you to have cancellation between infrared and the virtual diagram. So that paper, a lot of people know the history, was first proposed, was rejected by physical review letters many times. They eventually started with George Sturman. They end up with a, well, it's natural. Then when George gave a talk, Steve Weinberg got very interested. They worked together, improved the paper, rejected again. Because this is nonsense, right? How can you have this kind of phase-space constraint, you end up but still claim cancellation take place? Well, eventually the paper got published. It's interesting, go to website, take a look at that paper. So you can calculate those results in just a couple of hours. You can do it, all the calculations I'll show you for a moment. So this leads to the real life of the whole business of jet physics. They tells you, give you a footprint of quark. We never see quarks go on real, but from the structure, you give you the footprint of the quarks dynamics. But what is the theory behind it? How can this kind of cancellation between real and the virtual can take place to all order in perturbation theory? So constraint that imagine the cross-section is that you have a 2-particle final state, 3-particle final state, any number of particle state, final state in the QCD. You put the constraint function gamma with number of particles. If the constraint function equal to 1, sum all together, that's total cross-section. That's infrared state. Now you add a constraint function, you have to demonstrate the cancellation still take place. The requirement on this is exactly you have this gamma 2-particle finals. So you have a constraint function adding one more particle. If the one more particle is a collinear to any one of the early particle, or the particle added has 0 momentum, that means you could not tell difference. This situation, the one more particle versus the particle without this actual particle. So that's exactly conditions. If the constraint function satisfies this condition, then this observable with phase-space constraint is actually infrared safe. So I gave you a quick example. So the 2 jets, they actually see the experiment. This is very quick. From the lab, you can see the 2 jets. Then you can see the 3 jets. This particle is very early, no actual claim to be discovery of the gluon, because you see the 3rd jet, the QQ bar plus gluon. Then you can have an even higher nature, lab 2, you can see the much more particle in the final state. It's still a bigger fat jet known as the gluon jet. Question the calculation. Again, I start lowest order. E plus minus 2 QQ bar pair. You did a calculation before, that's fine. It's a Parton model picture, like it's finite, it has an angle distribution. So all 2 jets of the high order will be correction in the power of S. For total cross section, you integral the angle, and this is just the order of RFS over pi. But now you have phase-space constraint. You really constrain the phase space. What happened? Well, if you do it, the trick George Sturman and Steve Weinberg did. So instead of calculate, I have a real diagram, momentum go to 0, then virtual diagram. It's complicated, it's hard, because you're dealing with infinity. The trick is I define the cross-section as total cross-section minus the event not jet-like. So minus event when the third particle going in the large angle. So that means that calculation is much simpler. So when you do that, you eventually find the cross-section two jet one loop correction, the order bias with the angle between, this is the energy allowed the detector, from your detector never see everything. So that's a 4 pi, you need to cancel infrared divergence. Then this is the collinear divergence, infrared divergence, this is the collinear divergence, you have finite piece. So that was the calculation you can do very quickly. You know the total cross-section already. So you only calculate subtraction term, which you say the third particle is outside the jet cone definitions. It's a finite calculation, you can do it. So that now life becomes the real, jet physics become the real important observable at the LHC and many other observables. So the example is what the algorithm to define jet, because experimentally you see a bunch of hadrons. Theorists dealing with a bunch of partons. Now how you link together. And also you can see E plus minus, you start with no hadron. You just track down all the final state hadron, you organize it into the jet structure. But the hadron like LHC, you cannot do that. You start with a hadron that have a bunch of the hadron going to final state. You cannot integrate 4 pi to organize your event. So there are two classes of jet algorithm you should know. One is purely from E plus minus. The idea is there is no hadron to start. If I stay in the center mass frame, have no hadron to start with, but the final state have lots of hadrons in the 4 pi phase space. What I'm going to do, I combine any two particles together according to a criterion, add them together. If they're close enough, become the one effective particle. Then, so you keep combine them, then you end up with, say, if the invariant mass of 2 is larger than some value you define by hand early, say y cut. So that defines the number. By changing the y cut, your event could have a 2-jet event or 3-jet event, 4-jet event, depending on how you choose that. So you can, it's ambiguous. Who cares? Well, take advantage of that. You can test your theory. Apply to the event. You can test your theory if the theory is consistent with that. So that's known as the recombination of jet algorithm, mostly for E plus minus. Then depending on how you combine, you have different algorithms. I only give one here known as Durham algorithm. There are many different type of algorithm in the early days, but now we're dealing mostly the hadron-hadron collision. In a hadron-hadron collision, you don't have 4 pi phase space because you start with the hadrons. So in that case, we often concentrate on the produced particle in the large transverse momentum in a beam-beam collision configuration. So in that case, you define the so-called combined thing in terms of the rapidity difference of the two particles. That's the longitude direction, and azimuthal angle difference between the two particles. So that's a typical hadronic configuration of particle coming out. You have a transverse momentum, rapidity is longitudinal momentum, azimuthal angle. So you combine the two if they're close enough based on this criterion. Say you define R, you define that. So this is one of the criterion combined with some kind of fractional power P. Now if the P is equal to choose to be 1, known as the KT algorithm. If you choose P equal to -1, is known as the anti-KT algorithm. You heard about it. So basic idea is you produce a lot of particles, a lot of hadron in the final state. But I'm going to construct an observable without depend on any specific hadron. Only thing is I concentrate on some phase-based constraint. That quantity is perturbative calculable. So that's the second perturbative calculable quantity I gave to you without introduce any, say, distribution or non-perturbative physics, even though you have a constraint. Third one is known as a event shape. You will hear a lot from this lectures series this week. So when I look at the jet is some kind of event shape. I look at the event look like 2-jet or 3-jet. But there are also the observable was infrared safe, especially in the early days of E plus minus. There was a lot of data. People are not sure what can we learn from that. So one observable is known as thrust. Thrust is defined as it's a very complicated definition. You have n particle final state. You say I choose any individual particle, dot product to a direction. Then I'm going to maximize this quantity when the mu that's a direct t less than 1, much less than 1, the event looked like spherical symmetric. When the t close to 1, that means the event looked like a 2 jets. So by different choice of t, you are manipulating or you're controlling the event shape. The next lecture, Ian Stewart, he actually proposed the jettiness, which is another observable related to event shape. So those are the third example I gave to you known as event shape. So, but here is the homework. I'm done. Yeah, here's the homework. Then this line I gave here to prove with this constraint function, you define constraint function. I gave you criterion before. What the observable is infrared safe. With this constraint function, you can easily prove that thrust is infrared safe. Well, after all the example of the hadronic observable without identified hadrons, you see a lot of hadrons, but we don't know any detail of the hadron. But if we want to understand the physics or structure of a hadron, we like to learn more than that. So that's exactly the question I'm going to ask the harder questions. Is how to test QCD in a reaction with identifying hadrons. That will give you a chance to understand the internal structure of hadrons. So far, those observables wonderful. You test the QCD dynamics, but you don't learn anything about details inside hadrons. So we want to do that. So that's the challenge. And I told you anything with identified hadron is not perturbatively calculable directly. So the solution is the factorization. That's what we do next lectures. Let me stop here for this lecture. Thank you. This is a real big introduction.
Okay, yeah, we're if you're in the room and have a question, you're welcome. Right, you might need to move closer to this microphone so the people on Zoom can hear you. The people on Zoom would like to ask questions. I'll give you an opportunity in a moment. Type a question in the chat, or I'll let you unmute. So any questions for Jianwei? We have about 10 minutes. You might be pressing up.
There's an echo between.
So I had a question about like the very beginning when you were talking about how you could simultaneously diagonalize two of the generators in SU3. My question was, can you prove that without taking a specific representation first?
In principle, yes, there is two independent diagonal element. When I say matrix in that case, yes, we can discuss in detail how to prove it. There are two for SU3.
Okay. Yeah.
But those are the very convenient choice. Those are representation corresponding my state is 1 0 0 0 1 0 0 0 1.
Okay. So that means that there's no, at least for if you assume SU3 or the particles behave in some representation of SU3, then there's not going to be any wild cards where you couldn't simultaneously measure isospin and hypercharge at the same time.
It's over the states labeled by two quantum numbers, whether it's a hypercharge or the isospin or superposition of those two. That's fine. They're two independent, but they happen. The isospin and hypercharge is very convenient, especially isospin, because you can separate your state, the proton, neutron, in a different isospin state. That has a great advantage. You choose isospin as your quantum number.
Okay, I see.
Yeah, I have a question too. I don't know if they can hear me from here. Yes, so okay. Yeah, when you were talking about the two-jet cross-section in plus and minus, you were talking about how we have like this C coefficient depending on delta for the jet functions. And my question is if we can understand the C coefficient as a matching coefficient between the, I don't know, this Stefan Weinberg jet and the Parton Model cross section.
I actually, honestly, I didn't hear exactly clear because maybe mask I didn't hear very clear.
Yeah,
So
maybe-
let me say, you say there are two parameters have to have.
Yeah.
In that define the Weinberg, Sturman-Weinberg jet.
yeah,
The physics behind that, I have to choose the one parameter means I have to have sufficient cone size. So that means the collinear divergence will be inclusive, yeah, integrated over within the cone size. So then cancel the collinear divergence. Third one is the energy resolution of the order 4 pi. A second one. That tells you, because my detector, I cannot see any particle below say half GeV. So when you calculate in the Feynman diagram, within that region, whether the collinear or the real diagram radiation or the virtual diagram, you have to integrate over 4 pi. So they can cancel the infrared divergence. So those two parameters needed is exactly to help you to cancel the infrared divergence and the collinear divergence. The physics that for total cross-section, because inclusive enough, you never see sufficient detail. The real and the collinear, they just all cancel. It's a unitarity. But if you do that with a phase-space constraint, but I make sure my constraint is not tight enough so that in the collinear region and the infrared region still inclusive enough. Because I cannot resolve them to have to integrate over all of the phase space, so they cancel.
yeah.
So that's a physics behind it.
Okay, yeah, thank you.
Any questions from anyone on Zoom? Or Andrew asked a question.
Yes. My other question had to do with when you were defining dimensional regularization.
Sure.
And you were you combined two separate like partial cross sections, and then you showed that the epsilons canceled, and then you let epsilon go to 0.
Correct.
It looked like some of the finite pieces were gone as well. Is that just a product of your like subtraction scheme, or did they cancel and I missed it?
No, finite piece is important. That's your order of RFS corrections.
Uh-huh.
It could be possible the finite piece is equal to 0 in whatever scheme you choose. You just have a perturbation theory, you don't have the next leading order correction. But if the finite piece is not 0, that means that's your factory, the finite correction to your leading to your total cross section. Then also, if you continue on, you say the finite piece is so big, like instead of RFS over pi, say the first coefficient is 1,000. Then you know RFS at the say 100 GeV is roughly about 1/10. Then you say, oh, perturbation theory is bad because even though the divergence cancel, the finite piece is too big. So this is the reason people have been trying to calculate this order by order. To what we calculate here is one loop. People calculate 2 loop, 3 loop. Then the idea is that we know the QCD perturbation theory is asymptotic theory. Eventually, you know, instead of keep a conversion, eventually will blow away. So you never have, say, absolutely perfect prediction. There is always some uncertainty. Idea is, as far as uncertainty is sufficiently small, then you can make a good predictions. So people have been trying it. People have been trying to see whether to the point then the coefficient becomes bigger and bigger. So far we have not seen. They start to see a little bit hint at the fourth order. Some people claim that the coefficient becomes a little bit bigger. Yeah.
Okay, thank you so much.
Last call before coffee. Okay, well, there are 2 more lectures by Jianwei, so you have plenty of time to ask. I just wanted to comment, yeah, the calculating the Sturman-Weinberg cross-section is one of the first things my advisor made me do in grad school.
Yeah.
And it took me way longer than 2 hours.
Sure. When you calculate third order, yes, it will be longer than 2 hours.
So thanks a lot, John. Well, let's thank Jianwei again. Okay, I'll mute the question microphone. So if you're on Zoom, yeah, I'll leave this meeting open, but we'll be back in 30 minutes.
I need some air.
I'm not asking you a question.
Sure.
We had the 1 over epsilon squared and 1 over epsilon for the virtual and the real.
Uh-huh.
So you go to that slide.